So hello everyone, my name is Xuan, and today I'll be talking about bounded pitch inequalities for the covering problems, and this is a joint work with Professor Daniel Beanstalk and Professor Yuri Fanza. So first, let me quickly define what is a covering problem, as you probably already know. So essentially, they are the optimization problems over the set of 0-1 points that satisfy a set of covering-like inequalities. And when the number of inequalities is only one, we essentially obtain the minimum knapsack problems. So why is it interesting to study the covering problems? So there are many reasons. First, they appear in many applied settings. Also, they're relevant in computational IP. And lastly, there's still many theoretical open questions regarding their structures. In this talk, we'll primarily be focusing on a specific class of inequalities for covering problems, known as the bounded pitch inequalities. So the pitch of an inequality with non-negative coefficient and non-negative right-hand side is the minimum number pi, such that the sum of the pi smallest positive entries of the coefficients is at least the right-hand side. So for example, this inequality here has pitch 4 because you have to take 4 of the strictly positive coefficient to achieve the right-hand side. So of course, you might ask, why is it worth studying bounded pitch inequalities? Particularly because there have been many results showing very nice properties of them. So here I listed two by Daniel Beanstalk and Mark Zuckerberg. So the first result here relates bounded pitch inequalities with CG closures. In the second result here, they gave an algorithm which can produce a polynomial size LP that satisfies all inequalities with pitch less than or equal to pi plus 1 from an LP that satisfies all inequalities with pitch less than or equal to pi. So besides Beanstalk and Zuckerberg, there have been many other hierarchies introduced in the literature that also was able to achieve the same result. So in this talk, I'll be looking at three aspects of pitch. So in the first part, I'll be looking at the relationship between bounded pitch inequalities and bounded coefficient inequalities. And next, I will show a polynomial time algorithm, which approximately separates over the set of inequalities with bounded pitch. And lastly, I will give a lower bound on the extension complexities of an LP that satisfy all inequalities with bounded pitch. And I will show that this lower bound grows superpolynomially in the pitch. I should mention that from now on, we'll be assuming that all the inequalities have non-negative integer coefficient. Now for the first question. Simply by the definition of pitch, we can observe that when you have an inequality with coefficients bounded by k, then its pitch is also bounded by k. And this can be easily seen from the following example. So here all the coefficients are 1, which are exactly the smallest positive integers. And now if you take 5 of the ones, you'll be able to sum up to 5, which is exactly the right-hand side. So a natural question to ask next is, how about the reverse? A trivial answer here is no, because you can easily come up with a very absurd example like I'm showing here, which have a really high coefficient but only has pitch 1. So we need a better way to ask the question. So instead of focusing all the inequalities out there, we'll be focusing on something called undominated inequalities. So a pitch pi inequality is undominated if it cannot be written as a conic combination of other inequalities of pitch less than or equal to pi and valid for the minimum knapsack instance defined by the original inequality under consideration. So now if we go back to the counterexample we looked at it earlier, and that inequality is dominated actually because it can be written as a conic combination of the following two inequalities as listed below. So now we can ask a slightly smarter question, which is, if you're given an undominated inequality with bounded pitch, does that mean it has bounded coefficients? And now the answer is a little bit more complicated than a trivial yes or no. So it is folklore that an undominated inequality with pitch 1 can only have coefficients 0 and 1, and they will take the following format. And it is shown in Beanstalk et al. That if the inequality has pitch 2, then its coefficients are bounded by 2, and they can take the following form here. And what we show is that if the pitch is 3, then the coefficients will be bounded by 6, and they can take these two forms. So it seems like there's a pattern, and probably for pitch 4, the coefficient will be bounded by something like a 12 or a 24. But 12 or surprise, actually, as your pitch get higher, your coefficient is no longer bounded. This seems like a really nice little cute result, but why does it matter? Why do we even consider these problems in the first place? And the reason is that in Beanstalk et al., they gave a polynomial time algorithm that solves the epsilon separation problem over valid inequalities with bounded coefficient. So our hope was that if bounded pitch is the same as bounded coefficient, then their algorithm will directly implies that there is a polynomial time algorithm that solves the approximate separation problem over bounded pitch inequalities. So note here that we're not really talking about exact separation problems because that problem is NP hard already for pitch 1 inequalities. So let me just quickly explain what is approximate separation. So here I have an inequality represented by the green line. So for the exact separation, when you're given a point, you would like to know if it is falling into the green feasible region or it's outside of the feasible region. But in the approximate separation problems, when your point is in the green region, your algorithm will be able to tell. Similarly, when your point is in the red region, your algorithm is also able to tell. However, when your point is just slightly infeasible, meaning that it's in the white region in between, then your algorithm might be making mistakes. So our result here is that although bounded coefficient is not the same as bounded pitch, their algorithm still indirectly implies the result that we want. So the idea is the following. We've shown that to separate over inequalities with pitch less than or equal to pi up to certain precision epsilon, it is enough to separate over bounded coefficient inequalities up to a different precision. Note that this bound on the coefficients and this new precision level do not really depend on the underlying min-map instance that we're considering. So indeed, as an example, if you have a point x bar which violates a pitch 4 inequality, denoted by the green line here, and their precision level epsilon, you can show that there exists another inequality with bounded coefficients and pitch less than or equal to 4, for which x bar violates under a different precision level. And this new inequality essentially can be obtained as a CG inequality with appropriate multipliers depending on the pitch, the bound on the coefficients, and as well as on the precision level you desire. So lastly, let's look at pitch from a different perspective. In particular, the complexities of a polytope that is being defined by all bounded pitch inequalities. So the complexity here will be measured by something called extension complexity. So extension complexity of a polytope, denoted as such, is the minimum number of facets of any extension of P, where an extension of a P is essentially just another polytope lying in a higher dimensional space who can be affinely projected exactly to your original polytope P. And here's our result. We've shown that there's infinitely many matrix A and pitch pi, such that if Q is a relaxation of the polytope defined as a convex hull of all the feasible 0,1 points of this particular covering problem, and Q satisfy all the valid inequalities with pitch less than or equal to pi, then the extension complexity of Q will be super polynomial in pi. And this result actually applies to any covering problems because any covering problems can be written in this particular format with the right-hand side being 1. So now let me demonstrate the proof idea through some pictures. So for the extension complexity community, a really well-known polytope is the correlation polytope because it has a high extension complexity. Not only that, if you look at certain inequalities valid for the correlation polytope, as denoted by all these blue lines here, if you have any polytope that is kind of squeezed in between this correlation polytope and this relaxation here, they will have high extension complexity. So now to use this result, what we need is that we need to come up with a covering instance that can be affinely projected exactly to the correlation polytope. And on top of that, this instance should have certain inequalities with pitch pi, such that those inequalities also exactly projected to the certain inequalities that are valid for the correlation polytope. And if those are true, then if you have any polytope squeezed in between these two, like blue and red polytopes, they will also have high extension complexity. And this is interesting because essentially this is the first lower bound result regarding bounded pitch inequalities, as compared to many more works on the upper bound. And the best upper bound is by Fioroni et al., which is exponential in pi. And although there are still gaps between the upper bound and the lower bound, they're not that bad. So let me summarize the result here on the last slide again, and thank you very much for your attention.